Okay. It has come to my attention that I didn't put any references in the last two lectures because I was so eager to get into the material. I apologize for this, and I've corrected my mistake. So here are some references. Okay. The spirit of our lectures is in the following reference, which has the title The De Sitter Musings, so there are many more references that you can find in there, but the rough spirit of the lectures is along those lines. So today we have the third and fourth parts of this series, and the first thing I want to talk about is a subject that has acquired the name the DS-CFT correspondence. And in the second part, I'd like to talk about a more local perspective of the De Sitter universe as viewed by an observer sitting inside of it, rather than an observer measuring the correlations produced by the full inflating spacetime, okay? Can anyone guess what these, just to get you in the zone, what do these letters stand for? It's one of these anagram, whatever it's called. Oh, very good. Okay, so we've all had our caffeine injections. Okay. And the references for the second part are given, for example, by papers like this. Or maybe, well, anyways, and many more. So just a brief recap. Well, any questions from the previous lectures or anything? Okay. Did anyone solve Yuji's homework problem? Yeah.
The last reference seems to be weird. No, there's one digit missing or something.
The what?
It doesn't work. The last reference.
Oh, this one? Oh, this one is a paper whose authors are myself, Denef, Monten, and Sun. So it's just a recent paper that I wrote, maybe the latest one, I forget. Okay. Okay. So, brief recap. So what have we done? We discussed the geometry and the symmetries of this universe, okay? And we studied small fluctuations that are populating this universe in the limit where the geometry is rigid. We tried to organize our results in terms of the Euclidean conformal group, because this was the natural symmetry structure acting on the geometry at large, okay? And finally, we started discussing some aspects of geometric fluctuations, where we understood that, at least from the point of view of late times, the geometry is organized in terms of a conformal structure of 2-3 tensors living at the scribe plus, the boundary in the future. And so just to give some feel for these degrees of freedom or these coordinates in the classical phase space, so this is a 3 by 3 symmetric tensor. And but it has 2 gauge symmetries acting on it, okay? So, for example, there's tangential diffeomorphisms that remove 3. We can use to remove 3 components of the metric, and there's also a sort of a local Weil rescaling that we can do that removes 1. So from the 6 components of the 3 geometry, we are left with 2. Okay, these are the 2 polarizations of the gravitational field. And similarly, for the momentum, recall that it had to obey its own conditions in order to satisfy the equations of motion, which were a transversality and tracelessness condition, which again reduces the 6 components down to 2. And so our phase space is really at each point 2 degrees of freedom times 2 degrees of freedom. Okay, so this is the gravitational data is consistent with what you know about linearized gravity, except expressed in a slightly different language that has to do with conformal symmetries. Okay, so that's the phase space of gravity, classical gravity. There should be a button for this thing as well. It would be, okay. Okay, so, and then we discussed what it would mean to have a probability, okay, a probability function for G naught itself. Now, this was not just an academic question because, you know, after all, if inflation is the right picture of the early universe, it was not just the inflaton that will be fluctuating, but also the geometry itself. And to make sense of these fluctuations and make predictions, we need to understand how to assign a probability distribution to the geometry, to the fluctuations of the geometry itself. Okay, so we introduced an object, which is a wave function of geometry at late times, right? We care about it at late times, and we said that this has to be a diff cross Bile invariant functional. And we also required that it had some sort of Gaussian suppression about the round metric on the 3-sphere in order for it to describe small suppressed fluctuations about what we can interpret as an empty asymptotically de Sitter universe. Okay? So these were some of our requirements, and I think I gave a possible mathematical example as a proof of existence that this kind of object can exist. Okay. So any questions about that?
Sorry, is it possible to estimate the symplectic volume of this phase space, and is it finite?
It's infinite.
Even if you include the back reaction and the fact that...
then it's impossible.
It is impossible.
Right, so perturbative, good. So there's two answers, and both are unsatisfactory. In the perturbative limit, it's infinite. In the non-perturbative limits, it's incalculable. I'll give an answer, however, in this higher spin, I might give you an answer that's a little more satisfactory. The question is at the heart of what is holography. What is complementarity, in fact? Okay, so in the perturbative limit, this wave function has a nice expansion, which we can write in a suggestive language. So I'm going to be schematic here. But basically, in a perturbative limit where our sort of fluctuations are small, we can express this wave function in a way that looks a lot like a conformal collection of correlation functions. Okay? This is just a statement about the fact that we are doing perturbation theory about the de Sitter background, and that at late times the conformal symmetries act purely at the boundary. So perturbation theory has to obey the symmetries of the background, at least at tree level, and the ward identities of these symmetries impose a structure on the perturbative expansion of the Bunch-Davies wave function, or the Hartle-Hawking wave function in the case of gravity. And what it looks like is a collection of correlation functions, okay? Sitting at different points, right? So our wave function seems to be organized in terms of a collection of correlation functions. This is also true for matter fields, okay? And one might wonder whether there exists a CFT, a Euclidean CFT that calculates these correlation functions. Pardon? Oh, absolutely. Yeah, sorry, I was being schematic. Thank you. So all of these things are non-local functionals. And there's, yeah, sorry, maybe this was too schematic. Yeah, thank you. So people asked the question, starting with several works, notably that of Strominger and Witten and Malacena and others, whether perhaps there exists an actual Euclidean statistical field theory that produces this set of correlation functions, okay? This was the idea behind the DSCFT, and it's a dramatic idea because let's remember how we produced these correlation functions in the first place. We had an interacting theory with a bulk interior where we have to integrate our vertices over all of time and impose some boundary conditions deep inside the Euclidean past, and that led to these type of endpoint functions. And the claim, right, so it's an essentially time-dependent problem, and the claim is that somehow all of these calculations can be subsumed into a completely timeless calculation that captures what we thought was an infinite cosmological evolution in terms of the properties of some statistical system. Okay? So the claim is that, you know, this was somehow we were fooling ourselves when we were doing these calculations, and the actual definition of the system was a box full of operators with an ensemble of possible statistical weights and correlations, and that ultimately this was all there ever was, right? So I'd like to emphasize that this is a rather radical idea, more so than anti-de Sitter space in a sense, because what we're trying to get rid of in this case is time itself. Okay, so this was an interesting idea. It was based on symmetries, and well, it comes with virtues. But it also comes with some problems. So the virtues are straightforward. I mean, if this is the actual way to think about an inflationary universe, if this is the definition, after all, a CFT is a rather well-defined creature, whereas something like a gravitational path integral is a famously ill-defined creature. Perhaps this is the way we should organize our understanding of inflation itself. Okay? So and perhaps in this new language, some of the puzzling features of effective field theory might be recast in a less puzzling way. If inflation occurs at very high energies where our approximations break down for semi-classical physics or perturbation theory or whatnot, there's no reason why this system should suffer from the same pathologies, right? So if the scale of inflation is high enough for all stringy heavy modes or any other particles that in the system play a role, and we really need to deal with a hot, stringy, inflating universe, we better have an idea of how to formulate the problem in a more general way. Okay? And finally, it's fun to think about questions about holography away from the ADS box. After all, we don't live in an ADS box, and somehow whatever it is that holography is, it has to be something that applies more generally. Okay? Now, that's more of a theoretical motivation, whereas the other two might be very practical. The problems that it comes with are, well, if time really is somehow an artifact, what we're saying is that in the interior, quantum mechanics is an artifact. And this is a deep and confusing puzzle, right? And something that we might worry about. This is the difference, the big difference with ADS-CFT, where both sides of the duality borrow the same time and Hilbert space, an inner product, and there's no puzzle about quantum mechanics. Now, if you find yourself trying to describe the interior of black hole horizon in ADS-CFT, you might find yourself dealing with similar problems. But let me not get, let's leave that for the discussion session. Okay? But more generally, at least the way I formulated the problem here, what I've made is a statement about a single quantum state, right? But maybe we would like to have a statement about an algebra of operators and at least a Hilbert space living on a constant time slice, a late time slice, right? After all, I started this lectures very deliberately talking about the conformal properties of late time operators of fields and the operator algebra, and I very deliberately emphasized the point that quantum mechanics is connected to non-trivial commutation relations of these operators and these shadow operators, okay? The fact that alpha and beta gave this delta function was at the heart of having a perturbative quantum picture. And for that, you really need a language of operator algebra. Now, there are, of course, in the sitter, so we can call this the wave function picture of DS-CFT, okay? Oh, and connected to this, we still haven't solved the other measure problem, which is fine. Given psi of g, how I still need to integrate over its argument to produce an observable or an expectation value, right? And I haven't told you how to do this calculation in telling you how to do this calculation. So we've at best solved half the problem, okay? So there's some virtues in puzzles. And I should say that since these type of arguments came from the consideration of symmetries, one could also consider other objects that transform under the conformal group. For example, one could consider at least in some perturbative sense, not the perturbative corrections of the wave function, but expectation values of late-time fields, cosmological expectation values of late-time fields in a quantum state that preserves the de Sitter symmetries, okay? Like this log that we calculated when we calculated the power spectrum of the CMB. And those things also have to satisfy the kind of symmetry requirements of the de Sitter group. Now, the reason people typically don't formulate DS-CFT in this language is that the operators that enter over here are not the usual operators we encounter in conformal field theory, right? So I have to insert here something that looks like a spin-2 gauge field rather than a stress tensor, because sort of the expectation value of a perturbative object is more like that. However, We'll see a little later, I hope, that there's a way of even interpreting these objects as canonical CFT correlation functions by exploiting something called the shadow transform. Okay, but I'll get there in a second. Any questions? So this is some conceptual overload over here, and so one should. So let's take a minute to digest this kind of thing, because it's as radical a theoretical statement as the observation that these kind of phenomena occur in the universe itself. Okay.
So I'm not sure why I'm here.
Oh.
Why your statement about quantum mechanics? Because in saying that, you sort of say that the CFT space is more fundamental than the original one, no?
I am saying that.
And so, can you elaborate on that, perhaps?
Your question is analogous to the question people ask in ADS-CFT, whether the CFT defines the bulk or whether they're two independent formulations. So the answer is we don't know. My suspicion is that things are defined. I'm being caught on camera now, but my suspicion and speculation, and it's purely speculative, is that the CFT defines the interior geometry. That this is really the only definition of the system. But this is a speculation, okay? Okay. But we'll explore, okay, good. But we'll explore this. But the way, okay, and now for a thing that I do believe, the only way to understand this is by studying concrete models, okay? So that's what we're gonna do now, okay?
So if you look at states which are small perturbations of the statistical invariant state,
yeah.
can you relate the wave function that you get to some quantity in the CFT?
So let's see.
I mean, this state is the statistical invariant.
This is the de Sitter invariant state. You're good. This is the problem of the single quantum state.
Yes, exactly.
Yeah.
Perturbatively around the state.
Yes.
How you solve this problem?
Be patient. It's at the heart of the problem, and it has to do with this operator Hilbert space versus wave function. So ultimately, we would not like just a theory of a single wave function, perhaps, because in perturbation theory, there certainly seem to be other states, even de Sitter invariant ones. But then we need to reformulate the problem a little bit along these lines. Okay, good. Okay, very good. It seems we're all in the same frequency. What happened to the eraser? But there was another one. This one. So all of these questions, I think, to be addressed, one has to build concrete models, and the simplicity of the models is justified by the difficulty of the questions. Okay? I hope that's a reasonable condition. So let's study a particular model. And we can continue our guessing games. Yes? Yes.
The CFT, which would appear here, would also have a different behavior over, for example, the one in ADS-CFT. I mean, the CFT would be different than those in ADS-CFT.
Right. So in ADS-CFT, at least in the Euclidean picture, what we require is unitarity under radial quantization. This is not a requirement here, because we're dealing with the unitary reducible representations of the Euclidean conformal group. This is a crucial difference in how quantum mechanics is organized in de Sitter versus Euclidean ADS, which is really trying to mimic Lorentzian ADS. This is what separates the two systems. Okay. Okay, so, model. I'm going to give you a model, or at least a model whose effective field theory looks hopelessly complicated. It's a theory consisting of an infinite tower of higher spin particles, okay, of which the ones that we care about that are common to nature are the first three, something like a photon, something like an inflaton or a Higgs particle, and something like a graviton. And the mathematical crutch that the additional tower of higher spinning particles is that it comes appended with an enormous gauge symmetry, because these are all massless, okay? So the Yang-Mills symmetry and the diffeomorphism symmetry are a tiny subgroup of a much larger gauge symmetry. And it was shown at the classical level that by Vasiliev and others that one can build interacting classical theories of these massless waves so long as the universe is either an asymptotically de Sitter universe or an asymptotically anti-de Sitter universe. Okay? Now, this is good news for the de Sitter context, because it's a model that has the vestiges of something that behaves well both in the ultraviolet and, well, the infrared is something that we can explore. Okay? The ultraviolet properties of this theory, given the infinite tower of higher spinning particles, might be better behaved than your typical effective field theory. Okay? So that's the motivation, and it's already good news in the sense that these kind of models, just to give a word that might be familiar to some people, these models have no moduli stabilization problem. One of the issues in trying to build these kind of vacua and string theory is that we have to deal with a host of massless fields or tachyons that run away, and we need to find mechanisms to give them mass. And these mechanisms typically take us beyond the realm of tree-level physics. This theory only has a single scalar field, and the scalar field has a positive mass. And so it's perturbatively at least stable. There exists a solution to the nonlinear equations of motion, which is an eternally inflating universe, and the kinetic terms of these gauge fields are all positive, the interactions are real, and the scalar is oscillating inside a well. Okay? What makes the theory complicated is that all interactions occur on the same footing. Okay? So this theory does not satisfy the equivalence principle. So it's a theory of gravity in the sense that there's a spin 2 particle, but the gravitational interactions are not universal and isolated from all of the other interactions. This is what makes it a complicated system, and why we cannot decouple some of the particles from the remainder. Okay? Very good. Now, another virtue of this model is that it really has a non-trivial, it has a non-trivial CMB, so to speak. If this was inflation, which it's not, the model would produce a very rich set of correlations in the CMB power spectrum. Okay? And moreover, the classical theory is just tractable enough that we can calculate in the effective field theory description at tree level the space of all non-Gaussianities at the cubic level. This was a calculation not phrased in this language, but a calculation by Jambi and Yin, who understood how to calculate, based on ordinary bulk calculations, the space of all non-Gaussianities in this universe. Okay, so we have some enormous amount of data to work with to guess what kind of CFT might capture these 3-point functions. okay? So this is interesting, right? We have a system which has some vestiges of completeness. I mean, it's a classical limit, but we can access tree-level physics. And we can calculate non-Gaussianities, okay? And we can ask, yeah. Do you have a question?
Yeah, I have a technical question. So in ADS, you would have to make some choice about the boundary conditions of the fields.
That's right.
So in de Sitter, I guess you don't need to make this choice? Or?
The choice is called the polarization of the wave function. It's what you choose the wave function to be a function of.
But at the classical level now, I mean, this is a classical...
This is a tree level. It's a tree level contribution. So remember when we calculated the wave function? I said that there's a perturbation theory for the wave function itself in terms of a Green's function that vanishes everywhere except a point. And we use the corrections of the classical equations of motion, perturbatively, to produce contributions to the wave function. This is the most direct adaptation of the Giombian calculation as calculating pieces, non-Gaussian pieces, of the higher spin de Sitter wave function. This is what they did, in a sense. Okay? And for the wave function, we're allowed to choose future boundary conditions because we're conditioning, given an initial state, on what the profile is at late times. Good. Okay. So, we have a very specific spectrum. We have a very specific symmetry algebra, and we have access to the space of all non-Gaussian correlations. It turns out this is enough to formulate a reasonable conjecture, okay, as to what this wave function we've been talking about is as a function of all the higher spin particles. But before I do that, let me mention what we might expect at the semi-classical level, the wave function to be a function of. So, these are the fields, and in the late time limit, what we care about is the analog of what I call the alpha operator, G naught, and all of these objects that transform nicely under the conformal group. And, well, what we find by solving, for example, the free Fronsdal equation for these higher spin particles. So Fronsdal, many years ago, wrote down the free equation of motion for these higher spinning particles, is a collection of objects that transform nicely under the conformal group, okay, that look essentially like sources for conserved currents in a CFT, okay? So the late time profiles of all these fields have an associated gauge symmetry, purely acting on the spatial boundary. For example, the profile of the photon, one can add a total derivative of a scalar function. The spin 2 particle, like we said, we can do a diffeomorphism. And each of these has a higher version of this gauge symmetry at the infinitesimal level, okay? And we can collect all of these particles in a clever way in terms of certain differential operators. Sorry. So let me write down the formula and then I'll explain it. Okay? So imagine you had a function that's bilocal, a function that takes 2 points on R3 and produces a number. And imagine that I take the 2 points to be near enough that I can do something analogous to a Taylor expansion, but in this case a functional Taylor expansion, where each coefficient in the Taylor expansion is itself a function. Okay? Then I can expand such an object in terms of a basis of differential operators, right? So if we discretize the points in space, for example, we could use the discrete derivative operator represented as a matrix, and so on and so forth. And the coefficients can be organized to transform nicely under the conformal symmetries and capture the physics of all these profiles. Okay? So there's a rather nice way to organize our configuration space, which we can call the Daszewicki configuration space, which is basically, I have this infinite tower of higher spin profiles. I can append derivatives, contract their indices with derivatives, and produce some rather large Hermitian matrix, right? And sort of different pieces of this matrix correspond to different profiles. For example, the diagonal piece is the scalar fluctuation. The slightly off-diagonal piece is like the spin 1 field, and so forth. I hope we're still on the same page. This is just a clever way to package all of these different profiles. And you might wonder, then, whether the full wave function of the theory can be written in a nice way in terms of this object over here. So the conjecture now, at least for the wave function, is the following. So again, let me explain the formula. So take this profiles, viewed as a matrix with elements x and y, each living on R3, and add to it the Laplacian, okay, and calculate the determinant of this matrix with a correction which subtracts in the perturbative expansion the linear term in B, so that when you expand it for small b, it looks like a Gaussian object in the B's. And the B's encode all of the profiles in the following way. Okay? In a more familiar language, you can call this the Predation Function of a free CFT with all currents sourced. Okay? Yeah. Which one? The very last thing? Yeah, sorry, let me write that again. Thank you. Please do that, because I'm a left-hander, and writing is not my forte. E to the n.
Can you write it really bigger somewhere?
Okay. Well, it's an important equation, so I'll write it. Okay. Okay, good. This is a good thing, because in order to explain this equation, I should probably make sure the equation is readable. Is that okay? Excellent. N is equal to the ratio of L de Sitter over L Planck. It's the dimensionless number that controls the strength of the interactions in the theory. And this object is conjectured to be the exact wave function governing the fluctuations in the Bunch-Davies state of all the higher spin particles. It is a remarkable formula that does a lot in providing evidence that something like, at least for this type of universe, something like a DS CFT picture might make sense. Okay? Because as I said, you can also view this as a partition function of a CFT, where we take the free theory, okay, and we add the space of all possible sources for n scalar fields that are invariant under UN and single trace or single summed. Okay? So, the claim is that at least, in this sort of picture, based on these non-Gaussian calculations, one can write the wave function of this universe, this expanding universe, as a function of all of these profiles of all these fields, is in the form of a CFT partition function. The nice thing is that it's Gaussian, even though I'm sourcing all these currents, right? It's Gaussian. And so I can do the path integral and produce an object which I can now start thinking about in a very general sense as to whether or not this is a wave function. Okay? Oh, these are for, sorry, yeah. So n, for these to be Gaussian suppressed fluctuations, these have to be scalar ghosts. People called it the SPN model in the beginning because they were ghosts. But you see, again, this is just a tool to generate the wave function. I'm not appending any Hilbert space or operator interpretation to these objects rather than them just being a machine to calculate the correlation functions. Okay?
Sorry, if you expand this B, you get all the fields, right, that you have.
Yeah, yeah.
Which had some gauge invariance.
The gauge, good, yeah.
So how do we understand it in terms of the B's directly?
Good. So the gauge. So what are the symmetries of a free theory? So take these scalars and multiply them by another of these bilocal things, okay, that satisfy the following equation, okay, viewed as a matrix object. So let's decode what I just wrote. So take the free theory, do a general linear field transformation of phi, allowing it to be non-local, because again, locality is not the key over here. And then what you'll get is a U and a U dagger here. And if you want to get back the original action you started with, what you need is that U conjugates the Laplacian to itself. So in the perturbative level, this space of symmetries is the space of transformations that conjugate the Laplacian to itself. That is the higher spin symmetry group, expressed purely in terms of the boundary behavior of the fields. And as a subgroup, of course, it has SO4, but it's an infinite symmetry. Okay? And notice that our wave function is invariant under these symmetries because, well, of the ward identities of correlation functions of a free CFT. But in the determinant, it has to do with the fact that the determinant has this cyclicity property. Okay? Very good. So now, we have this wave function. We think we know what we're doing. Let's get down to business. Let's try to calculate something. For instance, we could imagine calculating a generating functional for the space of all late-time cosmological correlation functions, okay, themselves. So take the expectation value of e to the trace. By the way, by trace I just mean, so trace AB is equal to integral d3x, d3y, ax comma y, by comma x, okay? So I'm sort of imagining these things as matrices with continuous indices, and traces are integrals, and determinants are determinants over this functional space, okay? Okay, good. So let's try to calculate this. And already here we see the puzzle that, well, in order to calculate this, I have to tell you what the measure of integration is, not just the wave function. So we're already confronted with the problem. But what we're going to do here is we're going to first do the calculation in a saddle point approximation. We're going to work in a semi-classical limit to get a feel for what the answer is, at least the leading order in the large n limit. Okay? And the assumption is that in the large n limit, whatever this measure is, since it's not going to depend on n, in the strictly infinite large n limit, we can just treat it as if it was flat. So what is the answer if we do this? The answer is rather indicative. So I'll first write down the answer, and then I'll discuss what it means. This is a nice exercise to do. So let me delineate the calculation. So psi squared is the determinant to the 2n squared. You write the determinant. Yes?
Can we be certain that the measure does not depend on n?
Yes, this is an assumption. But it's a reasonable assumption because this has to do not with the theory, but with the configuration space.
Because, for example, in matrix models, the measure produces terms that you need to take into account to get the saddle point.
But there you know what the fundamental degrees of freedom are. Here, we're doing the most conservative standard approach to semi-classical physics, where we're just saying my configuration space doesn't have an n dependence. In the problem you're measuring, and that's an important point, you're already dealing with a configuration space that manifestly depends on n. We'll get there. Good. So let's do the saddle point approximation. You see, if I had n particles in my system, then the measure would depend on n. That's what happens in what your example. Okay. Okay, so very good, very good. Okay, so let me delineate the calculation. So the determinant is psi squared is determinant to the 2n. We can write it as e to the 2n trace log Laplacian plus b. Okay, so we have e to the 2n Laplacian b. So this is a homework problem. And then we take a variational derivative with respect to b to do the saddle point approximation. So everything in the exponent scales with n, and we're going to look for the saddle. Now, when we have e to the 2n log Laplacian plus b, and we take the variational derivative, we get inverse Laplacian plus b, because the derivative of log a is a inverse. Okay? But then we have an a over here, and a 1 over Laplacian over here. So there's a rather straightforward matrix equation to solve it, the saddle point approximation, and the result of this is let me write it in a slightly more convenient language. Oh, here we go again. Okay. A result that looks almost identical to the original, except with the sign of n flipped. The flip in the sign of n has to do with this. When we take the variational derivative, we've got the inverse of the argument. Okay? And the relation between this a, which is a curly a, and this a, when you do the calculation, you can verify is just a conjugation by the Laplacian itself. Okay? The reason I did it is that now I can identify the answer, at least in the infinite n limit, as a partition function, again, of a bosonic CFT. And now, the measure of our bosonic theory does have n in it. So we have 2n bosons, because we have a 2n here, okay? So, at least in the semi-classical limit, where I can trust these calculations, because these came from doing Vasiliev calculations, and these were classical equations of motion, what we produced was a function, a generating function of cosmological correlation functions, that is invariant under the symmetries again, except it looks like the partition function of a bosonic free theory with 2n bosons. Okay? And we've produced now a more satisfactory object, physically speaking, because this is the generating function of late-time cosmological correlation functions. Now, what this allows us to do, given that now we have things like the things I was talking about in the beginning, or for various different spins, we have the whole collection of tree-level cosmological correlation functions, which are expectation values of these operators I talked about. Okay? It allows us to start thinking about what is the space of operators in a conceivable quantum completion of this model. But before that, let me make one remark about this conjugation. So one of the things I complained about in the problems of the SCFT was that there are no natural operators that transform like these spin 2 particles. So how is it that I'm claiming that a CFT partition function is producing the correlation functions of these kind of operators? And this has to do with another important piece of information, which is that in doing this non-local transformation of the sources of my B's, what I actually did was calculate the shadow transform of each profile. Okay? What the CFT people will call the shadow transform of each profile. So let me give you a little bit of information about that. So given an operator that transforms like a conformal primary of weight delta, I can calculate its shadow transform. And the transform is a non-local operation you can do to the operator, and it maps the operator to a new operator that behaves as if it was a local operator as well, because it's labeled by a single point x. So you take an operator of weight 3 minus delta, a local operator of weight 3 minus delta, you integrate it against the 2-point function of the operator of weight delta, you produce a new function, again labeled by a single point, and this new object behaves like it's a local operator of weight delta. This is again a connection between the weight delta and 3 minus delta, special relation between the weight delta and 3 minus delta. Typically, when we do radial quantization, we're not allowed to use these transformations because we need a radial ordering of our operators in the CFT. However, as I keep on emphasizing, in the case of de Sitter, because of the different group theory that we're using, we might be allowed to use these kind of non-local transforms to transform our fields. And now we can ask ourselves a rather interesting question. By the way, these shadow transforms, among other people, were introduced in a, let's see if I get this right, in a paper by Gatto, Grillo, and Parisi. Are there any CFT experts? Just to give the original reference. Is that correct?
Well, do you have a paper reference for that?
That was my question. Somebody please post a paper. I think Parisi was one of the authors. Gatto, Grillo, Parisi. Anyways, they're in the... There's a new modern paper on this by David Simmons-Duffin on these shadows, where he references the history. Okay, good. Now, we can ask ourselves the question, since we've been dealing with conserved currents, what is the shadow transform of a conserved current? Any guesses? Something rather interesting happens. The shadow transform of a conserved current takes the divergencelessness condition of the current and produces a gauge invariance for the shadow. Okay? So, say I have a conserved... right. Say I have a conserved current. And I take its two-point function, and I want to think about its shadow, which is also going to be a vector. So I can dot the index of the two-point function. So, roughly speaking, and this is just a schematic exposition, but you know, there's ways to make this sharp. If I consider this shadow operator of the conserved current, and I add to it some total derivative, then I can integrate by parts, and the derivative acts on the two-point function. And because of the word identity, it vanishes. And so there's an ambiguity in the definition of this operator, and this ambiguity is precisely a gauge transformation. So there's a clever way to repackage operators that look like the late-time profiles of higher spin fields in terms of shadows of conserved currents, which are more standard operators we can compute correlation functions for. Okay? Now, what this means, operationally, from the point of view of these Qs, is that now I can imagine building an operator picture for this higher spin de Sitter universe. Okay? So I'll give you an algorithm, and then we'll take a small break. Okay? I'll give you an algorithm and make some comments. So algorithm. Define a collection of Hermitian operators, Q. Okay? And out of them, by contracting with the spin S transverse trace set of differential operators, build a collection of currents. Okay? So we're building operators that live entirely on R3. Okay? So it's a box full of operators, and we're gluing them together via their index, UN, U2N index. And we're building conserved currents, things that transform like conserved currents. Okay? These are operators. And now consider the quantum state which is UN invariant and also higher spin invariant, where the higher spin acts on the Qs the same way that I talked about on the phis. Consider the Gaussian higher spin invariant quantum state on the Qs. Okay? Of course, I can write this in an operator picture as a linear combination of the operator Q and the operator d by dq. Okay? And now calculate, in the Q language, whatever you want, until whatever your heart desires, in terms of correlation functions. In the operator picture, of these currents, and then take the shadow transforms of these currents, which is an operation that becomes maximally simple in momentum space, where the shadow transform becomes multiplying the operator by a power of the momentum and the appropriate transversality object. So if we take the Fourier transform of this thing, you will note that our exercise show that the shadow transform becomes very simple in momentum space. So this is more efficient to do in momentum space. Okay, so, and the conjecture now, and I believe this is the appropriate conjecture for this universe, this DSCFT, this Vasiliev universe, is the following. The fundamental operator content of the theory are these Qs. There are, at each point in space, 2 n operators. Everything in the theory, in the effective theory, occurs in the large n limit by considering composites of these operators. Okay? The Bunch-Davies quantum state is defined with respect to this Gaussian wave function with a flat measure. Okay? So we solve the measure problem. Okay? And with that measure, we can calculate the full set of correlation functions of the late-time profiles of the effective bulk operators. So I've given you a complete, precise algorithm in the picture of operators of what the set of what could complete the set of cosmological correlation functions in this theory is. And one can check this conjecture, again, doing the 3-point functions, but not the ones with future boundary conditions, but the cosmological correlation functions at the 3-point function level. And there's very nice conjectures you can make about what, for example, the late-time 4-point function is, which ordinarily you would have to calculate by summing an infinite channel of higher spin particles, but in the Q picture you can do in a rather efficient way. Okay? So, the picture we have here, okay, so anyways, let me just conclude with some comments before the coffee break. Some slightly philosophical comments, okay? We started with what looked like a hopelessly complicated effective field theory, with extremely complicated interactions and everything interacting with everything and everything talking to everything. And it seemed like the most peculiar place to try to study these kind of questions. But once we understood the problem, if this conjecture is correct, once we understand the problem in terms of the actual microscopic degrees of freedom of the theory, the problem became maximally simple. Okay? So comment number 1. In order to ask the right question, you might have to understand what the right degrees of freedom are. And all of the difficulty of the bulk theory was encoded in the fact that we were trying to fake a theory of n operators Q into a theory of volume squared operators B. Okay? So comment number 1. Once what I believe are the right operators were identified, the problem became maximally simple. Comment number 2 regards gauge symmetry. What I have given you is a collection of operators acting linearly on a Hilbert space. So it's not just a theory of a single state anymore, because I could act on the state with my operators now. But I have to have these operators obey certain gauge symmetries, right? So really, there's another step missing here. First of all, I'd like to gauge this index over here. But also, another distinction between de Sitter and ADS is that we really shouldn't be talking about isolated points in a diffeomorphism invariant theory, or a higher spin gauge invariant theory. What we have to do is also, at the perturbative level, gauge the residual higher spin symmetry group as well. Okay? So, if we're doing perturbation theory about a fixed de Sitter background, what we should really consider in the end of the day are SO4,1 invariant observables, right? Because the isometry group of the background is still part of the gauge symmetries. So we need to consider diff invariant observables as well. What this means is that really, in the end of the day, we should only consider operators that are invariant under both of these symmetries. So for example, well, let me use the matrix notation again. We could consider something like trace Q Laplacian index Q and so forth, right? So invariance under, just 2 more minutes, invariance under the gauge, the higher spin symmetry is just another type of matrix invariance where we contract the spatial indices as well, and we end up with non-local expressions. What this means in terms of the actual content of the theory is that even though we started with a volume times n worth of operators, by gauging appropriately, we actually end up with what seems to be an order n number of gauge invariant degrees of freedom. Because if I have a matrix which is V by n, and V is much larger than n, the actual invariant data of this matrix is the shorter of the 2 diagonals, is n. Okay? But n is equal to something that's proportional to what we'll see in a second is the de Sitter entropy. Okay? So, to conclude, we started with an effective theory in its classical equations of motions, and we tried to motivate an operator algebra picture of this theory. And given the specific knowledge of the gauge symmetries and the effective fields, we ended up with a system that comprised of around n degrees of freedom. So Scribe Plus was fooling us when it had all of this volume worth of degrees of freedom. Anyways, so let's end here, and then we pick up in 2 minutes.
Okay, are there any quick questions? So I have a question about this diffeomorphisms at the boundary.
Yeah.
In ADS, usually those would
constitute global symmetries.
That's right. So in this case, you still want to mod out by this.
Yeah.
Well, can you explain
why we have to mod out?
That's right.
So it's because, well, think of it like this. Imagine you have a compact Cauchy slice, right? In order to talk about global symmetries in the theory of gravity, you need a boundary or something. If you have a compact Cauchy slice, all symmetries are gauge symmetries. And so you're only allowed to consider things that transform in the singlet representation.
Okay.
Now that includes the naive isometry group in a perturbative expansion.
Right. Okay, so there is no coffee right now, so we'll take a 5-minute break. The coffee break will be in 1 hour. So, okay, let's stop for 5 minutes and then we'll continue.